Let's wait for 2-3 minutes, then I will start. Okay, let's start. So I will just have a recap of the last problem solving session, whatever I have covered. So you might have got this particular PDF notes or that the YouTube link also. So mostly I was just starting with the basics introduction of the atmospheric physics, why we generally study the atmospheric physics, and then we uh, just go through, we just went through about all those topics which have been discussed in week one. I have not covered completely, but most of them are being covered, like the forces based on where is it being applied in a controlled volume, whether it is in the surface or over the body. Based on that, the forces can be classified. So these are surface forces, then body forces. Next, based on the frame of reference, forces can be classified based on the frames of references, like if it is a real frame or a pseudo. Means based on that, the forces can be classified as a real forces or pseudo forces or apparent forces. So pseudo forces can be also written as apparent forces. So as we know that if you have an inertial frame of reference, which is I would say, non-accelerating, or if it is a non-inertial frame or accelerating frame of reference, in both those frames, real forces will be always applicable. So in a controlled volume, whether it is in a rotating frame or a non-rotating frame, real forces will always apply. But in the rotating frame, in our case, because we are talking about the Earth's atmosphere, so Earth being in a rotating frame, so any controlled volume or any air mass, or I will not say air mass, technically it's the wrong term. If you take a air volume, a small volume, controlled volume, so that in that you will get some apparent forces, like which we have discussed in the last problem solving session, like the centrifugal force or the Coriolis force. The way of deriving the Coriolis force or centrifugal force, which is done in the NPTEL series is different from what I have derived, but ultimately same thing is there. So in a different way, I have just derived here. So fine. So these are the real forces. First, I have discussed these are the pressure gradient force. Why pressure gradient? Because ultimately, if you look at the result, the after derivation, the result which you have got is depending on the pressure gradient, delta P, delta X. So in the X direction, X, I have also discussed about the sign convention. So X is the eastward direction. So in the east-west direction, that particular direction, how the pressure is being changed is given by, based on that, the pressure gradient force per unit mass actually here, it is the acceleration is being derived. Okay, so similarly in the y and z direction, and finally you get this. So minus 1 by rho grad p. Grad is itself in mathematics is a gradient, right? And then I have talked about the sign convention. So if you go northward, it is the positive y direction or positive j cap direction. If you go from the center of the earth towards the outside of the earth towards the atmosphere, like this is your plus k cap or plus z direction. Opposite towards the center of earth you go, it is minus k cap or minus z direction. X is towards the east. Positive east or positive x direction is nothing but the eastern direction. So all these sign conventions I have already discussed. Then gravitational force, we all know Newton's gravitational force, so I'm not going into much details that they have covered. Then comes the viscous force, that is also somewhat known, but in terms of stress tensor, the same way, which the way we have derived the pressure gradient force, the same way this viscous force is being derived. But remember, this viscous force, whatever I have derived here, is for the laminar flow. It's not for the turbulent flow. For turbulent flow, the expressions change. Okay, so we don't need to look into it right now because there are many frictional forces like your viscous force, laminar flow. Then you can have, there are many things like you have a planetary boundary layer. There you have different force. Turbulent forces are there. That is also acting as a friction. Okay, and the third one is the viscous drag. So all those forces will be there in the atmosphere, in the real atmosphere. But for the simplicity purpose, I have just derived for the laminar. This is couple of things. So these three forces, which are those pressure gradient force, gravity, and your frictional force. These are real forces. It will apply in both rotating frame as well as non-rotating frame. Okay, whether Earth is rotating or Earth is not rotating, hypothetical case Earth is not rotating, there these three forces will always apply. Okay, but Earth, so Earth without rotation, you will have all these forces which I have derived. These are the momentum equations, Newton's second law. Okay, now is the Earth with rotation, where I have derived how you go from a rotating Earth, it's a non-rotating Earth to a rotating Earth, and we have finally got these expressions, okay, where you got your Coriolis force and your centrifugal force. And this centrifugal force is being combined with gravity to give you G star. Centrifugal force is having very little magnitude, although it is important for directional purpose and all, but it has a very little magnitude in terms of in comparison to any other uh, forces, okay, on the earth. So these two forces, Coriolis and centrifugal, are the apparent forces or pseudo forces, which happens or which acts only when you have a rotating frame. So simple physics, if you in physics, if you are from the physics background, you know that what is the difference between a centrifugal and Coriolis force. So you have a rotating frame and you have a mass which is stationary. You will find from center to the outside there is a force radially. So that is the centrifugal force. And if this mass is non-stationary, it is moving, then another extra force comes uh, with the centrifugal force, that is the Coriolis force. So in case of Earth, we have derived this Coriolis force in IJK, that is X, Y, and Z direction. But in the horizontal Coriolis force, I have not derived. Today we will see. And finally, these are the three momentum equations for the rotating, where you will have these Coriolis terms, okay, pseudo forces acting. And also, the combination of gravity and centrifugal force is also being discussed. And I think in the assignment one, there is a question which talks about what is the gravity in the poles, something like that. So for that, this concept will be important. So I have discussed it. You can see the video link or through whatever, uh, through the PDF also, you can understand. So you can see that. So it's just the combination of the gravity, which is acting towards the center of the earth, and the centrifugal force at any particular latitude, phi. So based on that, we have derived an expression, this E dash, the resultant gravity, and finally we have got something. Okay. And there is another thing in the assignment one, which is the geosynchronous satellite. So geosynchronous satellite means the time period of revolution of satellite is same as the Earth's rotation rate. So you can use this Kepler's third law, which I have shown here, to calculate the A. Remember, A is from the center of the Earth. So if you have to calculate the height, you have to subtract this radius of the Earth. And what is the radius of the Earth? It is about 6370 kilometers, almost roughly. So you will get a rough estimate of that question which is being given. Okay, so what I have not covered in the last class is that the horizontal Coriolis force part. It is important, maybe later. Then we will talk about the material derivatives today. Then coordinate transformation, very important because we don't use the Cartesian coordinate. We sometimes use the spherical polar coordinate, becomes easier. And fine, and other things that I think continuity equations are there. So we will see all those things. Okay, one by one. So let me go here. So if you see these notes which I am making, you will be able to solve the assignment questions based on those concepts. So just follow that if you can, or otherwise, if you just read the materials which have been provided by the NPTEL, that is also fine. From there also, you will be able to solve many questions. Okay, so for this is the week 2 problem solving section on advanced atmospheric physics. So those who are not familiar to this field, they can go to another course, which is the Introduction to, I think, Space, Atmospheric and Space Sciences. That is the basic course, fundamental course. Based on that, this course is developed. So one who has no idea can go through that. Okay, go through that lecture. And okay, fine. So let me start with the maybe the total derivative, the material derivative. That is better. So to start with, so you have total derivative. So why am I talking about total derivative? Because there will be another term which is called as the local derivative. What is this derivative and all those things we will see in details. Looks like mathematical but has some physical meaning. Okay. We also call this as the material derivative. Okay. So let me see the physical thing. So suppose we consider any particular variable, say T. Don't think it as a temperature. You can think it as a temperature field. It can be any other field. Okay, temperature, pressure, whatever. Okay, there is another field called the geopotential. So you can think anything. Some arbitrary variable t, which is, uh, of course, it has a spatial variation. That is, it is in x, y, z, the three coordinates, and finally time. Okay, so space and time. So this is varying in space and time. Okay, so this is a variable. So now, if at a point, say A, whose coordinate is mentioned by x, y, z, and t, and there is another coordinate B, where okay, let me write this. It's not y naught, z naught, and maybe some t naught, maybe or t. Let us write for the time being, and it has changed to x naught delta x, y naught plus delta y, z naught plus delta z, and t plus delta t. If suppose b is the coordinate and the time has also evolved, okay, the time has also evolved by delta t while the temperature is changing. We are noting some changes. Okay, so The small change between the temperature at A and temperature at B can be written as delta T, which can be partially written as, see, these are all mathematical things. So delta T into some delta T plus. Okay. Second is your delta T means partial change in that particular variable in the x direction times delta x plus partial change in that particular variable in the y direction, and finally the partial change in the z direction. Why I'm writing this, not the total change? Because it is simultaneously the function of x, y, z, and t. It's not a complete function of x. So that's why we cannot write delta t as dt dx into dx. That we cannot write. Okay, because temperature is a function of everything. So this is completely from the mathematical perspective. And if you now, I would say, differentiate with respect to time, so delta t by delta small t, which is time. So what you get? You get delta t del t plus, because delta t will be cancelled, delta t delta x, you get delta x by delta t plus delta t by delta y by delta t, and delta t by delta z by delta t. Okay. So now if you take a limit, because this is a small change, if you take a limit delta t tends to 0 on whichever variables having delta t, like this, okay, this and this. So if you put that, what will happen? You know, when you do this, mathematically we can write this as dx dt, right? The total change of x with respect to time. Similarly, the same limit delta y delta t can be written as dy dt, and delta z delta t can be written as dz dt. These are simple things, right? So dx dt can be written as velocity, right? Because this is x is some displacement, y is some displacement, v, and let this be w. So x is eastward displacement. So eastward displacement by time is zonal velocity. Okay, and then you have y, that is meridional, north south. So north south displacement with respect to time is v, meridional velocity, and dz dt, that is upward, so it's vertical velocity. So this is already been covered, we all know this. Okay, so finally what we can write is that, and also if I take this limit delta t tends to 0 on the left hand side, this term, you get the total derivative, that is total rate of change of some quantity t with respect to time, can be written as therefore delta t partial derivative of t with respect to time into u times delta t delta x plus v times delta t delta y and plus w times delta t delta z. Okay, so this, okay, let me go one step further. So dt d small t will be equal to, this can be called as a local rate of change of t plus, can we write this as v dot grad t? We can write, right? Because this is how the gradients and all things are defined. Okay, so we can write this. So what is this? So this is your total rate of change of some quantity t. Okay, and this thing is called the local change. So local rate of change of t. Okay, local rate of change of some t, and this is called the advective term. So what is happening physically? What is happening is that you have a station. Okay, here some column of atmosphere will be there on top of it. So one thing happens is that, suppose T is now the temperature. What will happen is that two ways the temperature will change in this column. One is it will automatically change on its own here. That is local change, delta T, delta small t. It will, the temperature will grow here based on the local conditions. Number one. Number two is that because of the winds, which will carry some, or these winds, which are suppose coming from a higher temperature region. Okay, there's some hot deserts in the summer, right? So from if the winds are coming from the hot deserts, you will find that the temperature will grow over this particular station. So that is being done by this. So those who live in some northern belt, like or Delhi or this UP or northeastern regions, so what will happen is that when you in the time of winter, suppose you get sometimes you see that the temperature is fine. Suddenly, after some times or after quickly after say 2 days, there is a sudden drop in temperature, and you see that it is windy, very chilled weather. That means wind is coming from some Himalayan region where there is already having some snowfall. So winds are coming from that lower temperature region, and it is advecting towards the towards your own region, and that is changing the temperature at your locality. That is through this term, the advective term. Okay, and another is the local. That is from the local factors because of your urbanization, because of some banal day-to-day variations. Some temperature will change. That is your local change. So the total rate of change of a particular suppose temperature is based on the local change, that is the stationary over that particular region, regional change, and the advective term coming from through the winds. Okay, winds carrying some temperature changes or something. Okay. So this is what is the physical meaning of uh, the material derivative or the total derivative. Okay, so total derivative simply mathematically total derivative is equal to local derivative plus advection term. Okay, one thing to note is that we generally write minus v dot grad t. If this minus v dot grad t is greater than 0, then we call that it as warm advection. Okay, and this minus v dot grad t, if it is less than 0, then we call this as cold advection. That is coming from the cooler region. There is a reason for that because we want, we generally calculate this. When you take some observation in a particular region, when people take observation of the temperature, what they do is that they flip the equation like this. Because we want at this locality, what is the change in temperature? So for that, you need this. This equal to dt by dt, the total rate of change minus v dot grad. Now, if you look at here, if this is positive, see the locality, in locality, your temperature will change. Okay. So in this way, it is defined. It is defined like this. Okay. Otherwise, you don't require this. I have just added an extra part. Just you can stop here. This is the actual equation. Okay. The total rate of change is local change plus the advection. Okay, so this is your material derivative. Okay, now if this is the condition, then can we rewrite the momentum equations further? So let us rewrite the momentum equation. It will be a good revision. Okay, momentum equations. Let's write one by one. Three coordinates are there. So in the x direction, the momentum equation was du dt, where u is the zonal velocity, right? Zonal velocity means east-west velocity. Can be written as therefore, if this is the total derivative, can we write this delta u delta t, local change in the zonal velocity plus you have u delta x, the advection terms v delta u delta y plus w delta u delta z. That is equal to your whatever the forces in the x direction. Like you have minus 1 by rho delta p delta x. Then you have your friction F for x. Also, you have Coriolis force. So you can write so 2 omega w cos phi minus v sin phi. What is phi? Phi is the latitude. You remember from the last session. Okay. Next is the momentum equation in the y direction, dv dt. Again, similarly, we can write delta v delta t u delta v delta x. So u delta v delta x, right? V into delta V delta Y plus W into delta V delta Z advection term, that is equal to minus 1 by rho delta P delta Y plus for Y. Centrifugal I am not writing because centrifugal is very feeble in magnitude, so I don't want to write right now. 2 omega U, I think sine phi. Okay. And finally, the third, the vertical momentum equation, dw dt. Okay. So this will be again delta W delta T, the local change in the vertical velocity, plus the some advection delta W delta T, delta X, plus V delta W delta Y and W delta W delta Z. This gives you minus 1 by rho delta P delta Z plus FRZ plus Coriolis 2 omega U cos phi. One thing we are missing. What is that? This is vertical momentum equation. So gravity is important. So it is the only momentum equation where the gravity will act, which is minus g. Why minus g? Because g is always acting towards the center of the earth. Okay. So this is the vertical. So if you have an earth like this, vertical means in this direction. So g is acting here. Okay. So this is the vertical velocity. So let me just write. This is zonal. This is meridional. And finally, this is your vertical momentum equation. So these are the Earth's momentum equations. And actually, whichever weather forecast or weather predictions you see are based on not only based on these three equations, there are many other equations, but these three are very fundamental equations for weather forecasting. But the problem, why weather forecasting fails sometimes is because of these adjective terms. Look at these terms. Look at these terms. U into delta U delta X, V into delta U delta Y, W into delta U delta Z. What is this? These are non-linear terms. These are not ordinary differential equations, first of all. These are partial differential equations. But even if it is partial differential equation, these are non-linear. So non-linear equations are generally difficult to solve. We use numerical methods to solve, or some wave spectral methods are there to solve this. But still, because of this very strong non-linearity in the atmosphere, it is very difficult to predict the weather. But still, today, at least in India, the weather prediction has improved a lot. Okay, based on very recent models and the structure changing in the models, it has improved a lot. So remember, these three equations are very fundamental for forecasting weather. So day-to-day weather forecasts which you get are based on these three equations. Along with that, there are other four equations. So let me just list down those. Fourth one is the ideal gas equation. So ideal gas equation we all know actually. So it's not a very yeah. So its ideal gas equation is coming from thermodynamics. Simple. It's P is equal to rho R into T, where R is the gas constant. So T is the temperature, P is the pressure, rho is the density. So this is the fourth equation. The fifth one is your mass conservation, which we will talk at the last, I think. Mass conservation equation. Sixth is similar to mass conservation equation. There is a moisture conservation equation. Okay, moisture conservation equation. And the seventh one, which we will see in the next problem solving session, or week 3, you have already maybe have seen this thing, which is the thermodynamic energy equation. Thermodynamic energy equations. These seven equations, out of which three already you know. The fourth one also you know, this one, the thermodynamic energy equation, because week 3 content is already there. You might have read, or if you haven't, you will see it. Okay, mass conservation we will see today, and ideal gas equation you all know. Okay, from we have seen it in 11, 12 we have seen, and after that. So based on all these physical equations, weather forecasting is being done. So now you know that how the weather is being forecasted and why it is difficult to forecast a weather. Okay, because of the non-linearity in any of these equations. Not here in the ideal gas equation, but you see that all these equations will have the non-linearity. Okay, so this is one of the things which I wanted to show. Okay, so these seven equations are called the primitive equations. Primitive equations. On top of that, many modifications can be done in a model, but these are the seven equations for weather forecasting. Okay, now next thing is that, let me see, so it's done. One question we can do, one question we can do, uh, just a minute, just a moment. Yeah, so, okay, so the question is, some network connection may be there. So the question is that a baseball, if a baseball player, so if a baseball player throws a ball in a horizontal direction, okay, if a baseball player throws the ball in a horizontal direction uh, for a distance of, say, 100 meter, okay, at suppose 30-degree latitude, and in 4 seconds, okay. Question is that by how much, by how much is it, this the baseball or the ball which is being thrown, is it deflected laterally as a result of rotation of the earth? Okay, important question. All right. So let's read the question once more. So it is saying that if a baseball player throws a ball in a horizontal direction, okay, yeah. So in a horizontal direction for a distance of 100 meters at 30 degrees latitude in 4 seconds. Okay. So it has given us the information about which latitude we are in, how much is the distance the ball has covered. Just a minute. Yeah, fine. In 4 seconds. So the time is also given. How much distance it has covered, that is also given. Question is how much it is deflected laterally. Let us understand this. So you're on the earth, okay, and at 30 degrees latitude, okay. So you are throwing a ball in a horizontal direction. Let us say you are throwing a ball in the x direction, okay. So why it should move laterally? The question is, they are saying that by how much is it deflected laterally as a result of the rotation of the earth. So they are saying that because of the rotation of the earth, if you throw a ball in the x direction, it will not travel in the x direction, but it will deviate. Okay, it will deviate. So what is the force which is acting on the ball, which is deviating it from the x direction? If you remember, that will be the Coriolis force. Right? This is the Coriolis force. So if you are, because it is dependent on the rotation, and for rotation there are two forces which can act. One is the centrifugal, and another is the rotation. But they are saying the lateral rotation. It's not saying that vertically what is the change. So any change in the lateral direction when you throw a ball on the rotating arc, it is the Coriolis force. Okay, so this is the concept. Now, how to start with? So, to start with, we assume that any all other forces are not acting here. Only Coriolis force is acting. So, we will apply the momentum equation. And since I have assumed, assuming, assuming ball is thrown, ball is thrown in x direction. Let us assume you can assume it in y direction as well. It will work. Okay. So thrown in x direction, suppose. So I want the displacement of the ball in the y direction, right? Because the lateral displacement we want. So I start with the momentum equation, which includes v, because from v we can go to y, right? Because v is dy dt. So ddt is equal to minus f times u. Now what is f? F is, let me write, is 2 omega sine phi. From where this f is coming, I will come to it right now. Okay. For this, let us take the concept of horizontal Coriolis force. Okay. So let me come to another topic, which is the horizontal Coriolis force. We have already derived three components of Coriolis force. But if you limit the Coriolis force in the horizontal direction, how it will look like? Okay. So simple. So what is the Coriolis force definition? Is minus 2 omega cross V. Right? This is the definition. Only thing we will do is that V will be horizontal, no vertical component. Okay. So if Coriolis minus 2 omega, and we all know, and I have shown it in the last session also, that omega has two components, that is cos phi in the j cap direction and sin phi in the k cap direction, only in the northern hemisphere. So we are talking about northern hemisphere. And you have u v w. I will skip. I will make it zero because it's a horizontal. Okay. So now if you do the cross product, you will get, it will be minus 2 omega I hat minus v sin phi and minus j hat minus u sin phi. K hat will not take because it is the horizontal. There will be a k hat component, but I will not take that. Okay. So F Coriolis force in the horizontal direction is 2 omega sin phi. Let us take a minus sign also. Okay. 2 omega sin phi, and you have k hat, or okay, fine. Let me write it properly. It will be minus bi hat plus uj hat. Okay. Now you can see that we can convert it into some way, that is minus 2 omega sin phi. Leave it as it is. Can we write v times k cross j and u as k cross I? Can we write this? Let's see. So this is I hat, this is j hat, this is k hat. We all know this rule. Okay. So in the cross product. So if you have k cross j, it is opposite to that. It will be minus I hat. Right? So minus I hat can be replaced as k cross j. Whereas k cross I, it is in the direction, so it will be j hat. So uj hat can be replaced as. So finally, in the vectorial form, we can write this as minus 2 omega sin phi k cross the v vector, and this is the horizontal v vector. So v horizontal is ui hat plus v j hat. Only the horizontal velocities, x and y velocities. Okay. So this 2 omega sin phi is called as f. Okay. Sometimes it is called the Coriolis parameter. 2 omega sin phi, called the Coriolis parameter. Okay. This is Coriolis parameter. Omega's value can be calculated, but Just remember 7.29 into 10 to the power minus 5 radians per second. Phi is the latitude. Okay, so this is what we generally take. Okay, so that's what we will be writing here for solving the question. Coming into the solution again. So come here. Where will you? Yeah, this one. Let's come here. So I'm writing dv dt is equal to minus f times u. The opposite one, negative. F is the Coriolis parameter and u. That's all. Okay. So next is dv will be equal to minus f u dt. You integrate it. One. So get v is equal to minus f ut. Okay. Again, dv dt can be written as dy dt minus f ut. Okay. So dy can be written as f ut dt. Integrate it once again because I want the y value of y. Okay. So y is minus h u t square by 2. So it is assumed that u is now not a function of time. Okay, so this is how we can write. And now just put the things. So it is minus 2 omega sine phi. U is, we will write that t square by 2. All right. So 2 will cancel. Okay, phi is what? Given phi is 30 degree. Latitude angle is 30 degrees. Sine 30 is half. Right? So minus omega by 2. U. U can be written as, say, it has traveled 100 meter in 4 seconds. So it will be 25 meter per second. So this will be 25. Okay, this will be 25, and time is 4 square. So you can write that. And finally, if you do all these calculations, so minus 7.29 into 10 to the power minus 5 into 25 into 16 by 2, this will be 8. Some way, if you do all these calculations, 25 into 8 will be 200. So it will be minus 7.29 into 10 to the power minus 5 into 200. When you do all these things, you will get something like this, 1.458 into 10 to the power minus 2 meters. Negative sign. All right. So we get minus, can be written as 1 point, roughly 1.5 centimeters. So this is the lateral deflection. Okay, this is the lateral deflection. So initially, we have thrown a baseball in the zonal direction, in the x direction. But see, there is a y displacement also because of the rotation of the earth, which is because of the Coriolis force. And that is what we have calculated. So it's better to use the horizontal Coriolis force formula and try to find out the lateral displacement. Okay, displacement is a vector. So already we have got a magnitude 1.5 centimeter lateral deflection. But what is this negative sign reflects? This negative sign reflects negative y. What is negative y? Southward. So we are talking about the Earth sign convention. So positive y is northward, negative y is southward. So it will be southward. So just check. We have assumed that this baseball is thrown in the plus x direction. Correct? Plus x direction. That is eastward direction. So any ball which is or anything which is thrown in the positive x direction in the northern hemisphere, we all know that that mass generally rotates or generally deflects to its right. Okay. Similarly, in the southern hemisphere, it will deflect to its left. Remember. So in the northern hemisphere, Coriolis force generally deviates uh, some control volume to rightward direction. So it is deviating rightward, and if this is your positive y, this should be negative y. So it is valid, right? The negative means you are getting in the southward direction. That means it is deviating southward or to its right. Okay. So this is one of the questions. Similar kind of questions. Question is there in the first assignment. Not exactly same, I am not saying that it is exactly same. So you must try in the same way, the way I have done this. So you can try in that way. It will work. Okay. So just try that way and see whether it is working or not. Okay. Fine. So this is the question which I wanted to show. Uh, what else? Nothing. From the I think from the week one, mostly things are covered. Okay. So and for the assignment also some extra things I have already covered. So I think it is mostly done. Okay. Now let's move to the week two one. The contents from the week two, where it is specifically about. So let me write. This is week two contents. So week two contents is based on conversion of Cartesian coordinate to spherical polar coordinate. Very important. Uh, Visualizing it is far more important. So it is extremely important thing. So I will show it. Just a minute. Uh, so, so now we will move towards the spherical polar coordinate. So the thing is that Earth is a we consider Earth as a spherical body, but actual shape of the Earth is oblate ellipsoid. It's not a sphere, but to some approximation we can consider that as your uh, as a spherical body, and hence apply the spherical polar coordinate conventions in this particular part. Okay, so just a minute, let me see. Yeah. So what will happen here is that, so let me just draw a figure so that it is can be understood. There is a large derivation of the spherical polar coordinate, but I will not touch upon that. I will just simply try the visualization method, which is being uh, which I have seen in the contents. Okay, so this is suppose a three-dimensional, I would say not a sphere, but a hemisphere kind of a thing. You can understand like that. Okay, so this is your your z direction, which is away from the center. This is your z direction or k hat. Okay, and this this is your phi. Not this one. I'm sorry. This one from the this is the radius of the earth. Suppose this is your phi, the latitude. Okay. Okay, so this part is your y direction, and this is your x direction. Okay, so uh, now if I just put a projection on this line on this plane, so this becomes your lambda. So what is the change? Earlier in the Cartesian coordinate, you have x, y, z, which has its own convention. We are converting this 3 into r, phi, and lambda. So lambda is longitude. We know very well that what is the longitude, okay, in the globe. Phi is latitude, and your r or z are same. Okay. So because you can see this is your r or radius of the earth, whatever you want. So this is the same in the same direction as z. Lambda is somewhere related to x, and phi is somewhere related to y. See, this phi is somewhere related to y, and this lambda is somewhere related to x. Okay, so this is the idea that we will convert it from XYZ coordinate to R phi lambda coordinate. Okay. So the best way to do is that, so let me just start with this. You have the momentum equation du dt. Remember, this is in the vectorial form. That is, u consists of u, v, and w. Okay. So u vector. So it is ui hat, ej hat, w, k hat. So can be written as I hat du dt plus j hat dv dt plus k hat dw dt. But when we are converting our coordinates, this is fine for the Cartesian coordinate. But if you are converting coordinate to spherical polar, then I hat changes, j hat also changes, and k hat also changes with time. Okay, not with time actually, but total derivative will change. So total derivative means with not only with respect to time but also with respect to space. Plus, so what we will write is that u into di hat by dt plus v into dj hat by dt plus w dk hat by dt. Perfect. So this extra has come from the conversion of Cartesian, the normal XYZ coordinate to spherical coordinate. So our aim will be to understand how this I hat is changing in the Earth's frame of reference, how J hat is changing with it, and how K hat is changing. Okay. So this is the main perspective or main aim of conversion of the coordinates. Okay. So let us see. Let us consider first D I hat D. Let us understand and let us visually see what is actually happening. Okay. D I hat D. Let us focus on that because these three things we have to focus on. Okay. Not the other. Other things are already known. Okay. So I hat. What is the direction I hat means? So if you have a two-dimensional arc, I'm just making this quadrant. Okay. So this is the northern hemisphere, one part. Okay. So what is I hat? I hat is this, right? This. If you have a point here, you have a cross. That means it is going into the paper. That is the I hat direction. Correct? East west. Okay. So this east west direction is your I hat. So how is it changing? Is it changing with X? Is it changing with Y? Is it changing with Z? With time, we assume that it is not changing. Okay, I hat is not changing with time, definitely. Okay, so we are only assuming that this changing with X, Y, or Z. Let us see. So, okay, let us consider this. Okay, let us consider this. This is your Earth. Okay, this is some kind of structure of the Earth I am trying to make. Okay, now if you have a I hat here, suppose. Okay, this is I hat. This is perfect because this is east, this is west. Just think about it. This is the rotation of the Earth. If this is the rotation of the Earth, then east should be this and west should be this, and I hat direction is pointing towards east. Okay, pointing towards this is the unit vector that's tangential to a point. So this should be the I hat vector here. Tell me now. Okay, so this is suppose at some latitude. Okay, now in another latitude, this will be like this. Now tell me one thing. This will be another I hat. Is it changing at this point? Or if you take another latitude further northward, is this I hat changing with Y? Because this is the Y direction, right? This is your Y direction, northward. So in the Y direction, is I hat changing? The answer is no. See, they are all tangentially in the same direction. Just try to visualize it. Okay. So we can write it I hat is not changing It's not changing with y. Okay. Is it changing with z direction? Let's see. So which is the z direction? So suppose let me see. How will I? Okay. So let's make another figure the same way which I have made like this here and here. Okay. Now if in the z direction, that is, now if I go much more to the top, right? Because this is the z direction, right? Okay, as you go far away from the surface. So red one is the surface, this green dashed line is the atmosphere. As you go more vertically in the atmosphere. So now, if you make this I hat again, okay, so somewhere here, suppose this is your I hat in general. Is this I hat change if you have I hat here? That means top of this. So how will I represent is much more important. Suppose you have here. So you have an eastward direction here. Now, on top of this, suppose here, will this I have changed? No, because in the z direction, it will be remaining the same. The I hat vector will remain the same. So I hat is again not changing. You have to visualize on your own that then only you will understand. It's not changing with z also. Okay, it's not changing with z also. So I hat is not changing its direction with y, not changing with z. It's not changing with time t also. Okay, but it is changing. Whether it is changing with x or not is the question. So let's make another diagram to understand this. Okay, let's make it here. All right, make a small something like this. Just try to visualize because it is difficult to, because it's a visualization technique, so it's difficult to say whether you understand or not. Okay, so now in the x direction, which is this, right? This is east, this is west. Yeah, I've already shown. So at this point, this is your I hat. Tell me, at this point, your I hat changes? Yes, right? So at this point, at the end, very end, your I hat changes. So it becomes something I hat plus some delta I hat, let's say, correct? So I hat is only changing, is only changing in x direction. Okay, this is important. I hat is only changing in the x direction. So let us see that how we can make the coordinate transformation for I hat. Okay, so let us see how to write the I hat. So d I hat by dt can be written as u delta I hat by delta x. Okay, because your delta I hat by delta t is gone. Okay, and so delta I hat by delta y is 0, no change in y. With z, no change. With time also, no change. So all things are 0, only this is what you left behind. Okay, so u delta I hat delta x. This is what we need to find out. So how to calculate? U is fine. U is okay. It's already there. What I need is delta I hat delta x. Okay, so that is what our main point is. Okay, so let's see. What I do is that this part, this this area, let us take this area, okay, and simplify it like this. Can we write like this? Yes. Okay. And this is your, say, this axis, this one. Okay. So this I have written like this. So this is your delta lambda because this is your lambda direction, right? Delta lambda longitude. Longitude always varies in the east-west. So this is how your delta lambda is defined. Okay. Now I change the color to understand. Let me rub this and try to make it. Okay. So you have this, you have this, okay, some curvature has been given. Okay, now on top of this, if I just try to calculate, so this is your delta lambda. Okay, this point I hat is this. At this point, your I hat is tangential to this. So this is I hat plus suppose delta I hat, the change. Okay, delta I. Okay, so now this vector, if I shift here, what is this become? This is I hat. Now, if this is delta lambda through angles and all, you will be able to understand that this will also be delta lambda. Okay, these are vectorial things. You can see triangle equality, inequalities, and theorems. And finally, if you apply triangle's law of vector addition, you get the resultant as this. Okay, the resultant as the towards the uh, axis, this axis. Okay, towards the axis, you will get the resultant vector. Okay, and this resultant vector is nothing but delta I hat. Fine, because you can see just the subtraction of this magnitude. Okay, okay, and what is the magnitude of this? These vectors, small vectors which I have drawn. These are one because unit vectors. I had magnitude is always one. Remember this. Okay. So if I apply here, you know that angle, okay, angle into radius is equal to r. So we know all that this is valid expression. Arc is equal to angle into radius. Same thing we will apply here. So the magnitude of this, which is 1, times delta lambda is this arc delta I hat. Okay, delta I hat, which is this one, is this any of this, so 1 times delta lambda. Great. This is one of the equations which we get. That means delta lambda is equal to delta I hat. All right, fine. Now this entire thing, this entire this blue line which I have, this curve which I have, is nothing but delta x. Correct? Because it is in the x direction, some small change in x. Okay. So again, if I apply here, so what will happen is that, see, this cross section is coming from here. Let me do it again. Okay, this cross section is coming from here. So you have a latitude phi here, and what I am doing is that this is what I have drawn here. Okay, so if this is your radius of the earth r, then what will be this? If this is phi, then this line or this will be nothing but r cos phi, where phi is the latitude. Okay, so too many things I know, but just think about it right now or later, whenever you are doing. So I'm trying to put some effort in understanding that why we are writing like that way. Okay, so this r cos phi, okay, this radius into this delta lambda is nothing but delta x. The change in this one is delta x. Now delta lambda is delta I hat. So r cos phi delta lambda is delta I hat. We have already got this. So what I need, delta I hat by delta x, which is nothing but 1 upon r cos phi. Is it okay? Now this is nothing but the magnitude. But what is the direction? Direction is towards the what do you call it? So direction is here. Let me. So if this is your Earth's surface. Sorry. Okay. If this is your Earth's surface, your I hat, if you carefully look at, your resultant vector is in this direction. Okay. Now I need direction. I have already got a magnitude. I need direction. I already know that this is your J direction. This is your J hat, and this is your K hat. Some phi is here. This is your K hat. We all know this. Okay. from the sign conventions. Okay. If this is 5, this will be also 5. Now, if this is now j hat in this direction, what will be the j hat's component? So the direction of delta I hat, which is this one, will be, so this is your j hat. If this is 5, this will be 90 minus 5. So it will be j hat sine 5. J hat sine 5. But k hat, if this is 5, okay, this is 90 minus 5, this is 90. So what will happen is that this will be minus k hat. So minus k hat into cos 5 we can write. So just write that. Okay, I hope it is clear. See, this is your j hat. This is 5, angle 5. So it will be j hat sine 5 in this direction. K hat is positive here. Minus k hat will be in this direction. And there is a phi here. It will be minus k hat cos phi. That's all. This is the direction. Therefore, your delta I hat by delta x, this thing I'm writing as 1 upon r cos phi as the magnitude, and the direction is j hat sine phi minus k hat cos phi. Okay, this is your expression. So now this is the expression of delta I hat. So di hat dt, what will it be? It is u delta I hat delta x. Therefore, we can write u divided by r cos phi. Okay, you have j sin phi minus k cos phi. This we have got. What is r? R is radius of the earth. Perfect. This is how you build up DID. One is clear. One step is clear. Okay, let's go to the second one. Let's see how j hat is varied. Okay, so if we go here and look at the expressions, I have got this already. I need dj hat dt and dk hat dt. Difficult again. Let us see whether we can visualize it or not. So dj hat dt, for that we need to understand j hat is a function of what? Is it a function of only y, like I hat is a function of x, not y and z, or is it a function of both the things? So for that, let us see. Somewhat easy, I would say, but still it is difficult to visualize. I will try to make my best efforts to understand. Okay, so this is suppose your surface, and you know what is the j hat direction. So this is your j hat direction. Tell me. So this is your y direction, right? This is your y direction, positive y direction. Here, this is your j hat. At some point at delta y distance, your j hat becomes this. Is there a change between j hat? Yes, there is a change. You can clearly see there is a change in the direction, maybe in the magnitude. Okay, so sorry, this should be. So this is phi, this is some delta phi or some delta y distance. So j hat is changing with y. Okay, so it is a function of y for sure. Okay, no problem. Is it a function of say z? Let's see. So make a diagram like the same way. Is it a function of z? So for that, let us make a delta z. This is your delta z. This is your y direction. So suppose here you have a j hat. Okay. Here you will have a j hat here. Are these same? Yes, the direction is same. Magnitude is also same. So j hat magnitude will be same, right? So because it's a unit vector. So j hat does not change in z direction. Correct? Understood? See, the j hat remains same. But let us see whether it changes in the x direction or not. For that, again, we have to visualize in a very different way. Then only we will understand. Look, So let's make it something like this again, so that it is visually understood. We can understand it. So this, and let's see this. Okay. And this is your delta x, correct? Delta x direction. This is delta lambda, suppose. Now, if I put j hat now, so what will happen? This is your j hat. Now, this is your j hat. See, there is a visually you can see that there is a difference. Okay, so something like this. It is happening something like this. With x, it changes levels. Okay, so this is also a j hat, another j hat, but there is a difference. Okay, so that difference we have to uh, see. So j hat changes with x. So unlike I hat, which only changes in the x direction, not in y and z, j hat changes with x and y, not in z. So j hat is a function of y and x. Okay, so this is the difference between j hat and I hat. Let's compute these differences and try to get up an expression for dj hat dt. Okay, will be somewhat difficult to visualize, but let us try. Okay, first let us make the easiest one, that is j hat changing with y. This is what the first priority we will try to visualize. So it's easy to visualize this. Okay, so whatever I have drawn earlier, so making a quadrant, and this is your radius r, this is your phi, this is some delta phi, this is some delta y, and your unit vectors here it is j hat, here it is some j hat plus delta j. All right. So now, what will be the what I would say the direction of these two? So if you just shift the vector here, you will see that it will come out like this. Something. I'm sorry. This should be very difficult to. Okay. So something like this. Okay. So and what I will promise this. So this is your j hat plus delta j. This is your j hat. So if you just put it here, you will see that the unit vector is some way in this direction. This should be the direction of the j hat, delta j hat. Sorry. Okay. I will make it once again for your visualization. So the thing is happening is that so this j hat is something here, and j hat plus delta j hat is somewhere here. Okay. And if you look at the direction, is your delta j hat. So this is your j hat, this is your j hat plus delta j. And again, this will be again delta phi. Okay, this one, this angle will be here. All right, but look at the direction of delta j. It is purely in this direction, that is towards the center of the earth. Okay, so the direction, the direction of delta j hat by delta y is in negative k. Okay, so it is in the negative k direction because this is your k direction. So negative k is the direction of delta j hat delta y. But what is the magnitude? Question is, what is the magnitude? Try to see here. You know that magnitude of unit vector is 1. So 1 times radius times angle is the arc, which is delta j hat. So 1 is this. Second is, take this bigger area, which is delta y is equal to r delta y. Right? Because this is the radius r and this is delta phi is nothing but delta y. So delta y is equal to r into delta j hat. So delta j hat by delta y magnitude will be nothing but 1 by r. Therefore, delta j hat by delta y is minus k hat divided by r. This is your delta j hat delta y. Okay, just try to visualize, try to do it on your own. Then only you will understand. Look into this after the problem solving session. Just look into it. If you are really trying to understand that how it is happening. Okay, so just try to visualize this and try to understand what is happening. Okay, fine. Second one is your delta j hat by delta x. This is somewhat complicated. This is somewhat complicated. So I will try to make the figure. I think this figure is already made in the what you call as different books. Also in the content, week 2 content, it is there. So I will try to make it, try to make you visualize that what is actually happening here. So this is your actual axis of rotation, and you have something like this. Okay, let's see whether make it or not. Okay, so this is one of the curvature of the y. Okay, and another one is something like this, right? This is this I have some. So this is some kind of a segment of the sphere. Okay, and at some latitude phi from the center, this is the center. This is your r. All right, and this is your delta x. Correct? This should be the delta x. This is also some delta x. Okay, and let's see whether we can make it like this. This is some delta lambda maybe. Okay, and this is r cos phi. Whatever we can make, let us make it. Okay, now what I will do is that I will extend this and try to put some lines so that we get projection kind of a thing. Okay, so what is happening is that your j hat is here. Okay, and I will try to connect it somewhere. Okay, maybe just increase the axis somewhere here. Okay, so we will get to know what is happening. Something like that. Okay, just I'm connecting it. It's a wrong way of. Okay, let me try it here. Okay, this is one. This is the second. Okay, so your j hat, we change the color again. Your j hat is here. One of the j hat is here, and with x, the j hat direction changes something like this. Okay, so this is suppose j hat. This is suppose j hat plus delta j hat. All right. Now this is actually equal to this phi. Okay, but this one, which is actually we require, this is not delta phi. This is some delta, some angle c, suppose delta c. Okay, so let us write this one something like this. So you will try to see that it is happening like this. Uh, this is your thing. Let me visualization is very difficult. So this is here and this is here. So j hat is here and j hat plus delta j hat is here. Why? Because if you see these two, you can see that it initially looks like this. It will come out to converge this. So j hat plus delta j hat, if it is here and j hat is here, so it will be here and it will be here. Okay. So in this way, you can just try to visualize. Okay. So something like this will happen, and the inner angle will be delta C. This will be your delta J hat, and this delta J hat, you will see that it is in the, so this delta J hat will be in the minus I z direction. Why? Let me show you why. So what we are doing is this. Okay, see, this is your x direction. This is your plus I hat or plus x, whatever you want. What is happening is that this is what is happening. Okay, so this is your j hat and this is your j hat. So yeah, this is what is happening, and this is your delta j hat. This bold arrow, and you can see that its direction is opposite to this. Okay, so this will be in the minus I hat direction. Just remember. But what will be its magnitude is the question. See, this line, this magenta or purple line which we have drawn, is actually perpendicular to your r cos phi, right? This is perpendicular. So this magnitude, whatever I have written here, this part will be r divided by tan phi. How is it happening? Very simple. Just see. This is your angle. This is your perpendicular. This is your r cos phi. Okay. This is your r cos phi, definitely. So, I'm sorry, written the wrong way. This is the perpendicular. Sorry. Okay. So, this is your perpendicular. This is your base. So, we know that base divided by, sorry, perpendicular divided by base is your tan phi. Okay. So, your base your base will be nothing but perpendicular divided by tan phi. So here the perpendicular is r divided by tan phi. So base is this violet line, this one. Okay, this is your base. So this becomes r by tan phi. This projection, I think it is already there, but I am trying to show you again. So now let's talk about this part. Okay. So one is that your delta C into 1 is nothing but delta J hat from here, the same way which we have done earlier. In the same way, this part can be written as the delta C into R by tan phi is equal to your delta X. So delta C is nothing but delta J hat R by tan phi is equal to delta X. So delta J hat by delta X is nothing but tan phi by R. Therefore, delta J hat delta X, magnitude and direction both will give you tan phi by R minus I hat. Okay. Very difficult to visualize. Just try to see later if you can. So dj hat by dt will be equal to u delta j hat by delta x plus v delta j hat by delta y, because these two j hat varies in x and y, so that's why we can write this. So it will be minus u tan phi by r I hat plus or minus v k hat by r from the previous expressions. Okay, so dj hat dt we have already found out. Okay, bit difficult to visualize this one. This is easy compared to this. This is easy. This is also somewhat easy to understand. Okay, so I would rather say that you try to see all these things and try to do it on your own so that you can understand. Okay, so one thing I want to comment here. One is that this one delta delta x. So in the spherical polar coordinate, the I hat, the unit vector in the x direction, eastward unit vector, is depending on only u. Okay, the motion, right? The motion is dependent only in the zonal direction. So it is dependent on the zonal motion, either east or west. So depending on the sign of u, depending on sign of u, the I hat will guide, will be guided. Okay, so remember this. I think some questions are there based on that, so that's why I thought to. Similarly, j hat unit vector in the y direction depends on both u and v. So both northward or southward or east west, both. Okay, it depends on both. Number two. Okay, fine. Let's go to the third one. That is how k hat changes. Third is how k hat changes. Okay, d k hat dt. Again, we will start by making rough diagrams to try to see that k hat changes in which direction. Is it x, y, or z, or some combination of both, like j hat. So let's try that and see how we can derive those things. Okay, so let's do that. So let's try uh, in the x direction. Okay, so for x direction, you need something like this. I was making like this only. Okay, so this is your x. Tell me now here, where is your k hat direction? So if suppose this is your x direction, your k hat direction, or just look at this. Your k hat direction here will be in this direction, k hat, and here it is here. So you can clearly see that k hat is changing its direction with x. At one place here, k hat is in this direction. At other place, it is in this direction. So there is a clear change in directions. So k hat changes with x. Okay. Or if you want to do it here, you can see this is the direction of k hat, and or over here, this is the direction. So k hat is changing for sure with the x. What about y? Is it changing with the y? Let's see. So for y, only this will be enough. So suppose these are the 2 points. This is phi, this is delta phi, this is delta y. Where is the k hat? That is from center to outside. So this is your k hat, this is your k hat. Clearly changing sign. So k hat changes with y as well. But what about z? So again, you just do like this. This is the z direction. Then is k hat changing its direction? No, k hat will remain same in the z direction. So it is never going to change with z. So k hat is not changing with z. I think this is easier to visualize and it will be clear. Okay, so k hat is therefore a function of again x and y, just like j hat. Okay, so let's calculate again. Easier is the y one, how to change how k hat is changing with y. So we will look into that first. Okay, so for that we need this diagram. Okay, and these are the couple of things. This is your k hat. Suppose this is your k hat, and this is your k hat plus delta k hat. This is your delta phi. This is your phi, and let's make this k hat come here. Okay, and if you just look into it, this is your direction of the resultant. That is delta k hat. If this is phi, or this is suppose phi, or this is delta phi suppose, this will also be delta phi because this is the angle, right, between them. So this is delta phi. So again, magnitude of the k hat is 1. So can we write 1 into delta phi is delta k hat? Angle into radius is arc. Okay, fine. And this is your delta y. Okay, so this is your arc, radius of the arc. So r delta phi is equal to delta y. So arc here, delta y is r times delta phi. And delta phi is delta k hat. And this is delta y. So delta k hat by delta y, to check the magnitude, it will be 1 by r. But in which direction? Delta k hat's direction is in the positive y direction, which is plus j hat. So delta k hat by delta y is plus j hat by r. That's all. Very easy expression. Okay. The next one will be in the x. When you are going into x direction, it is somewhat difficult, but let us see. Let us try. Okay. Let's try this. How we can write the in the x direction how k hat is going. And for x direction, you know that what we are doing is something like this. So make a plot like this, okay, and like this. All right. So let's take some different. Yeah, let's see something like this. Okay, and you know that your k hat will be always from the radius, radial direction. So this will be your k hat, and another will be something like this. This is k hat plus delta k. Okay, and in between this angle, let us say this is some angle delta c. Okay, this is your delta x level, you know. Okay, this is your phi. This is also known. This is r. Fine. These are also known. When all these things are known, can you write from this, and this? R, that is radius, times the delta c is nothing but delta x. One expression we can write. Now, what about the unit vectors? Can we combine them? Yes, we can. So it is something like this. Some k hat. This is k hat plus delta k hat. Look at the direction. This is your delta k hat. Okay, this is your delta k hat. And if this is your delta k hat, you can clearly see that it is in the positive x direction. Just you have to visualize it. It is tangential. Okay, so this delta k hat direction is in plus I hat. But that's all. So if this is one magnitude, this is also delta c. So delta c is nothing but delta k hat. In the same way, the way we have proceeded earlier, this is delta k hat, this is delta x. So delta x, sorry, delta k hat by delta x magnitude is 1 by r, and with direction is plus I hat by r. Therefore, dk hat by dt is nothing but u by r I hat plus v by r j hat. That's all. So these three will be utilized. So this is number one, number three. Okay. Next, this is number two, and the first one is number one. Where is that? Yes, this one. Okay. These three things we will combine and write the momentum equation in the spherical polar coordinate, where u is nothing but ui hat plus vj hat plus wk hat as du dt. We have written this expression already. I'm writing it again. Du dt I hat plus dv dt j hat plus dw dt k hat. Done. Along with that, we know that because of the spherical polar coordinate conversion, you need this d I hat dt plus v dj hat dt plus w dk hat dt. So what we'll do is that I will put these expressions from 1, 2, and 3. So from 1, this is from 2, this is from 3. All right. So if we do that, let's write that. Okay. So du dt vector will be equal to du dt. Let us let us write all the terms dv dt j cap plus dw dt k hat. All right. Along with that, you can write u. Now, what is di hat dt? We have already calculated, which is u by r cos phi into j hat sin phi minus k hat cos phi. All right. This is the first term. And what is its direction? Its direction was in the I hat, right? Oh, sorry, this is the direction is already written. Okay. Plus V times dj hat dt. What was that? Minus u tan phi by r I hat minus d by r k hat. And finally, w times dk hat dt. We just now have found out that is this. All right. So let's write the expression further and combine the I hat direction, j hat and k. So du dt will be equal to C. Du dt, okay, which are the I terms? This is, okay, minus uv tan phi by r, another is this, plus uw by r, I hat, plus dv dt, j terms, this. So it will be plus u square by r, sine by cos is tan. What are another j? J term, this VW by R, J hat. Then next dWdt. Okay, where is the k? Here is another k. So it will be minus u square cos phi goes. So it will be R minus this one v square by k. And that's all. So du dt, therefore, or fine. This is okay. You don't need to write it. So this is the conversion of momentum equation, momentum equation from Cartesian to spherical. Now, how will the each components of the equations looks like? It's very easy now. So I will just list it down. X component is du dt is minus uv tan phi. These are extra terms because of the spherical coordinate, plus uw by r, and the right hand side forces will all be same, minus 1 by rho delta p delta x, okay, minus 2 omega w cos phi minus v sin phi, whichever whatever we have derived, you can write frx, the friction, the same. Y component is dv dt plus u square tan phi by r minus vw by r is equal to with minus or plus, vw not, so it will be plus, I guess. Check it one. Vw by r is minus 1 by rho delta p delta y minus 2 omega u sin phi and fr1, the friction. And finally, the z component is dwdt minus u square plus v square together combined divided by r is minus 1 by rho delta p delta z minus g plus 2 omega u cos phi plus fr z. Okay, this is the z component. So these are the three components in the spherical polar coordinate. You can always change this delta p delta x, delta p delta y, delta p delta z in the spherical polar coordinate. How? Now your delta x is nothing but r cos phi delta lambda. You can write like this. Delta y is r delta phi. Okay, and finally delta z is nothing but delta. You can change it like this way, or otherwise you can keep it like this. So these are the how you can easily calculate the spherical polar coordinate. Better to use this equation, try to remember. You can't derive it when you try to, uh, suppose in your exam, you cannot derive it. But if you practice it, you understand it, these equations, if you look into it and try to write it down, it will be clearer to you. Okay. And whenever you need to see that how it is being derived, just look into these way. I have gone into much details, I think, compared to the whatever content is given. So just try to look into it. You will be able to understand. I'm sure you will be able to understand how these are being derived, how the directions are being uh, seen. Okay. So it's better to draw it like this and try to see whether it is right or wrong the way I have shown. Okay. Just try that whenever you get time. Okay. So this will clear your understanding. So that's why I'm asking. Okay. So I think this is good enough. One more thing is the mass continuity equation. I will try to show that. And okay, in the mass conservation, this is the last topic I will cover right now. And so there is, I think, a lecture which is based on Eulerian approach and Lagrangian approach. So Eulerian approach is something similar to what we have derived the pressure gradient forces and your laminar flow viscous force. Okay. There is a mass conservation equation in the Eulerian form that you can see it in the content. I will try to use Lagrangian approach. Okay. So mass conservation equation using Lagrangian approach. So Lagrangian approach means you are tracing the thing. So how the mass is changing with time. So you just do ddt of this. You are not writing it as delta means local change plus advective changes. So Lagrangian approach. Okay, you will understand. So it's easy. So okay, mass conservation. The major theory is that mass can't be created nor be destroyed. So the total mass in a controlled volume at any time will be constant. Controlled volume will remain constant. This is the mass conservation. In conservation means that the quantity is conserved. So if the amount of mass inflow is more, the mass outflow will also be similar. So that the mass in the controlled volume will remain same. So let us consider an arbitrary shape, or you can consider a cubic shape, whatever you want. Okay. So better is to take a cubic shape so that because you are looking into a Cartesian coordinate, so just make this. This is x, this is y, this is z. Make a cube short or a cuboid, I would say. Okay, where this is your delta x, the volume is like this. This is your delta y, this is your delta z. So the mass is inside is delta m, let us say, and let the density is rho. Okay, so the volume will be rho delta x delta y delta z. So density of not only this control volume, the entire space having density rho. Okay, and the with volume if you multiply, this becomes your delta M. Now what I will do is that I'll try to see how the total rate of change of mass changing. And I know that conservation equation shows that d dt of some delta M is always zero. Mass is not changing, it remains constant. Right? So this is what we will try to see. And this is the mass conservation equation. So let us derive it further. So d dt of rho delta x delta y delta z is equal to 0. So let's go to the first step. What it will be? D rho dt. You know the basic rules of differentiation. So that's what I'm doing. Plus rho d dt of delta x. Again, delta y delta z plus rho d dt of delta y. Get delta x delta z plus rho d dt of delta z. So you have delta x delta y that equal to 0. So d rho dt delta x delta y delta z plus rho you can take outside. What you get here is the d dt of delta x delta y delta z plus d dt of delta y delta x delta z plus d dt of delta z delta y delta x. All right, this becomes equal to 0. What I do is that we divide by delta m, or which is equal to rho delta x delta y delta z. If I do that, what will be the first term? 1 by rho d rho dt. Okay, because this thing will be cancelled by this, plus rho will be cancelled, and your 1 by uh, so your yeah, so this d dt of delta x. Okay, fine. So let's write it. Better is to write. So uh, rho delta x delta y delta z d of delta x by dt into delta y delta z. So delta y delta z goes, rho goes, plus rho d dt of delta y divided by rho divided by delta x delta y delta z. These are easy to do, you can understand. So delta x delta z will be cancelled, rho cancel. Third term, rho d dt of delta z. So you have delta y delta x in the denominator. You have the volume and density. Density cancels. This cancels. So finally, you get 1 by rho d rho dt. Now what I do is that d delta x by delta t can be written as delta u by delta x plus similarly here delta v by delta y and finally delta w by delta z. Put that equal to 0. Take a limit and see delta x, delta y, delta z tending to 0. You put this here. So you get 1 by rho d rho dt plus delta u delta x plus delta v delta y plus delta w delta z will be equal to 0. Or in much more better way to write is del dot v is equal to 0. This is in the Western form. This is the simple mass conservation equation. Important thing is that in and in compressible flow, so your d rho dt is actually becoming 0. So you get del dot v is equal to 0. This is one of the point from the mass conservation equation. So this is the mass conservation equation. whether you do Eulerian approach or Lagrangian approach, you will come to this. Okay, so that's all. I think, yeah, 7:50. So I think I should stop here. There's too much of mathematics in this course, so it is important that you also give some time and try to look into these things once again. And yeah, if any question is there, you can ask right now, or otherwise we can leave or we can meet in the next class. So in the next session, I will be trying to look at the assignment one and assignment two. I mean, I will discuss the answers because tomorrow is the last date, I think. After that, only I can tell you the solutions. So we will discuss that. Along with that, we will try to look for the energy equation and yeah, I think scale analysis and all those things are there. Yeah. So yeah, yeah. Yes, yes. बोलो. Okay. हाँ, यूट्यूब में मिल जाएगा. आपको वो मिला है मतलब प्रॉब्लम सॉल्विंग सेशन का एक लिंक मिला होगा आई थिंक. तो वहां पे आई थिंक कोई यूट्यूब लिंक है. वो देखा आपने? हाँ, तो वो यूट्यूब लिंक अगर क्लिक करोगे तो ऑटोमेटिकली पहला जो लेक्चर है मेरा मेरा वाला वो आपको मिल जाएगा. तो तो आप उसको एक बार देखिए. मैं कहूंगा कि इससे पहले उसको देखिए. ये भी आ जाएगा उसके बाद क्योंकि आज ही मैं अपलोड करूंगा. तो कॉन्टिन्यूअस चीजें बनेगा मतलब. नहीं, इससे पहले एक एक हफ्ता जो पिछले वीक में मैंने एक वीडियो अपलोड किया था और ये सेकंड, ये दूसरा. ओके. ओके. हम्म. ये नोट्स भी अवेलेबल होगा. एक ड्राइव में आई थिंक वो नोट्स भी है. मैं दोनों ही अपलोड करता हूँ. तो ठीक है. हाँ, कोई डाउट होगा तो पूछना. तो नेक्स्ट क्लास में हम लोग डिस्कस कर सकते हैं. बिल्कुल. ओके. ओके.